Hi, in this video, I'm going to show you how to solve the shortest path problem using Dijkstra algorithm. So suppose we have a graph. This graph can represent towns A to H and the roads connecting them. So the markings could be the distance of the road or the cost of traversing each road or the time it takes to cross from one town to another using that road. So the shortest path problem is a problem on finding the shortest path from initial vertex to terminal vertex. So in this problem, we're going to find the shortest path from vertex A to vertex H using Dijkstra's algorithm. So let's start. When you're finding the shortest path between two vertices using Dijkstra's algorithm, the first step is to create a table with rows and columns representing the vertices of your graph. So for our given graph, we have the vertices A, B, C, D, E, F, G, H. Now, these rows here represent all the vertices that we are going to visit or we are going to label. On the other hand, the first column represent the vertices that we are going to visit. Since we're starting at vertex A, obviously, the distance from vertex A to itself is 0. So, the first label that we have is 0 sub A for vertex A. So this is now a permanent label for A. So what we're going to do is we first visit A. So looking at our graph, from A, we can see that we can visit vertices B, D, and C. So to visit vertex B, the distance is 1. To visit vertex D, the distance is 5. While to visit vertex C, the distance is also 5. Take note that the rest of the vertices F, E, G, and H cannot be visited directly from A. So what we're going to do is we're going to write the cost of traversing those edges coming from A. So to go to vertex B from A, we have 1 sub A. Vertex C, we have 5 sub A. And vertex D, we have 5 sub A as well. The subscript means that we are coming from vertex A. On the other hand, E, F, G, H cannot be visited directly from A. So by convention, we're going to use a really large value for that. Usually, we use the infinite symbol. So here, infinity means that we cannot visit these vertices directly from A. So now that we have temporarily labeled the vertices B to H, we can now get the smallest value, which is 1A, on vertex B and permanently label B. So since B has the lowest temporary label, we permanently label B. So we write 1 sub A and we put it in a box to denote that we are permanently labeling B. So this time, we are going to visit vertex B. Now, from vertex B, if we look at our graph, we can visit vertices A, D, and F. But since A is already visited, or it already has a permanent label, so we don't need to go back to vertex A again. So from B, we can go to vertex D. So the temporary label of D becomes 1 plus 5. Now, if we look at the value of the label of D, 5 sub A is smaller if we come from A than if we come from B, because if we come from B, the temporary label for D is 1 plus 5, which is 6. So since this is a bigger temporary label, we will not use it and we will just retain the temporary label 5 for D. So we will keep this label 5A because the temporary label given by B is greater than that given by A. Now, similarly, we can reach F from B. So that becomes the label of B1 plus the cost of traversing the edge B to F, which is 5. So 1 plus 5 is 6. So we can give a temporary label now for F, which is 6. 6 is less than the infinite value. So we will now use this as the temporary label for F, 6 sub B. Again, we use the subscript notation B to denote that this label is coming from the vertex B. Now, any other vertices cannot be reached from B. So that means that the temporary label of these vertices are infinite coming from B. Now, since C already have a temporary label 5 sub A, then we will keep that label. The rest, the label remains infinite. So basically what we're trying to do is we find a label for each vertices on each iteration, and then we get the smallest possible label. For the next step, we choose the smallest possible label. So we have two candidates for that. C, which is 5A, or D, which is also 5A. At this point, you can choose either C or D. It doesn't really matter which one you take first. So let's say we want to take C first. So we are going to permanently label C. So I'm going to write 5A and put it in a box to mean that this time the label is permanent. Now, we are going to visit C. From C, looking at the graph, we can see that we can reach vertex A, D, and E. Again, since A already has a permanent vertex, then we no longer need to concern ourselves with going to A. But for D and E, we can reach D by adding 30 on the label of C, and we can reach E by adding 6 from the label of C. So, to reach D from C, we have 5 plus 30 or 35. That's greater than the temporary label of D, which is 5A. So we're keeping this label 5A. On the other hand, we can reach E from C with a label 5 plus 6 or 11. Since 11 is smaller than infinite, then we're going to use that temporary label, 11 sub C. Now, since vertices F, G, and H cannot be reached directly from C, then we are going to keep those temporary labels for F, G, and H. So we're just going to copy 6B, infinity, and infinity. So at this point, we have already visited three vertices, vertex A, B, and C. So again, we repeat the iteration by choosing the next vertex with the smallest label. At this point, that vertex is the with label 5 sub A. So we are now going to permanently label D as 5 sub A. And we are now going to visit D. Looking at the graph, from D, we can reach vertices except for those who already have permanent labels. So we can reach vertices F, G, and E. So the temporary label of these vertices will be the label of D plus the cost of traversing vertices from D to that vertex. Alright. So to get to F, we have from D we have 5 plus 15 or 20. But currently the temporary label of F is 6, which is smaller than 20. So we are going to keep this label and will disregard the label that is given by this iteration. So we are going to copy again 6 sub B. Now from D we can also reach G. So that's 5 plus 6, 11. Currently the label of G is infinite, so we can replace that by 11D. H cannot be reached from D, so the label of H will remain infinite. E can be reached from D, so that gives us 5 plus 12, 17. But 17 is bigger than the current temporary label of E. So we're going to retain this label of E, which is 11C. So as always, when the current temporary label of a vertex is smaller, then we will retain that temporary label and we'll just disregard the label given from that iteration. Now, up to this point, all the vertices with labels are vertices A, B, C, and D. The next vertex with the smallest temporary label is now F with label 6 sub B. So that label will now become permanent. So we permanently label F as 6B. And then we are going to visit F. So from F, what are the vertices that we can reach? From F, we can reach G and H. So we no longer need to bother ourselves with B and D since those vertices already have permanent labels. So from F to go to H, we add 10. So currently the label of F is 6. So plus 10, that's 16, which is smaller than infinity. So we write here 16 from F. On the other hand, we can also reach G with plus 3. So F is 6 plus 3, 9. And that is smaller than the current temporary label of G. So we replace this by 9F. Now, E cannot be reached from F directly. So we will keep the label of E. Next, the smallest temporary label is G. So we are going to fix that label. So we write 9F for the permanent label of G. So we are now going to visit G. And then we look at the vertex G. From G, we can reach E plus 2 or H plus 4. So for E is plus 2. So the temporary label of E is 9 plus 2, 11. But that is also the same as the current temporary label of E. So there's no need to replace that. So we can just use 11C. On the other hand, for H, that is plus 4. So 9 plus 4, 13. So meaning, since it's smaller, we are now going to replace the temporary label of H with 13G. Again, the next step is choose the vertex with smallest temporary label. So that's E with a label of 11. So we now fix E and we are now going to visit E. From E, the only vertices that we can visit are C, D, and G, but all of these vertices already have permanent labels. So, no need to replace the label for each. So, the temporary label of each will now become a permanent label. So now, all of our vertices have been labeled. So what does this label means? The labels are our notation for the shortest path of this particular vertex from A. For example, the shortest path from E is coming from C. But we already know that the shortest path from C is coming from A. So that the shortest path from E, if we backtrace the path, will be A to C and then C to E. The shortest path from F is 6 coming from B. But we already know that the shortest path from A to B is the direct path A to B. So, if we trace back this path, the shortest path from A to F is A to B and then B to F. The shortest path from G is coming from F, but we already know that the shortest path from F comes from A. So that's A to F and then F to G. So now if we want to summarize these informations, so what we can do is we can list all the vertex and the shortest path from A. So the shortest path from A to itself, of course, is A to A. And that has length 0. The shortest path from B, according to our Dijkstra's algorithm, is A, or rather 1A. So that means that's a distance of 1 coming from A. So that's A directly to B. Similarly for C, the shortest path is 5 coming from A. So length of 5 and the path is A to C. For D, it's 5A as well. So as you can see on our illustration or on our graph, these are the shortest path from A to B, from A to D, and from A to C. So for D, that's of length 5 coming from A. For E, we have 11 sub C. So meaning, to get the shortest path from A to E, you must come from C of length 11. So the length is 11 and a path coming from C. But we already know that a path coming from C has a shortest path A to C. So we have A to C, and then from C, you can go now to E. If you look at our graph, so this is A to C, and then this is C to E. So that's the shortest path from A to E. Now, the shortest path from A to F is 6 coming from B. So this is 6 coming from B. We already know that the path from B is A to B. And then from B, you can go to F. Looking at our graph, so this is A to B, and then from B, you can go to F. So that's the shortest path from A to F. Now, what's the shortest path from A to G? 9F. So a length of 9 coming from F. So we already know that the shortest path from A to F is A to B and then B to F. So now you just have to add F to G. Taking a look at our graph, so that's F, A to B, B to F, and then F to G. With a total distance of 1 plus 5 plus 3, which is 9. So that's the shortest path from A to G. And finally, the shortest path from A to H is 13G. So meaning from G, you go directly to H. So of length 13. So that's A to B to F to G and then finally to H. So in our graph, starting from this time G, you can now go to H. So that's the shortest distance from A to H. So that's A to B and then B to F and then F to G and finally G to H. So that's how we find the shortest distance from an initial point to any of the points in our graph. And that is called the Dijkstra algorithm.